Hello. Okay, so today we are going to start the first section of Chapter 4. Chapter 4 is all about forces in one dimension. And today we're going to look at the relationship between force and motion, so force and acceleration, and how mass comes into play with that. So let's talk about what force is first. So a force is a push or a pull exerted on an object. And this force can cause objects to speed up, slow down, change direction, so basically change the acceleration as the object moves. So a force exerted on an object can cause the object's velocity to change, right? Because a change in velocity is a change in speed or a change in direction. And we know that a change in direction or speed, which is a change in velocity, is acceleration. And so basically forces cause acceleration. So that's like one of our key concepts for this section. When we look at forces, we need to know what the force is applied to and where the force is coming from. And so we say that the system is the object on which the force is being applied, and then the external world is basically everything around the object that's exerting forces on it. And there are two main types of forces that we're going to discuss that come from the external world. First is a contact force. So this exists when an object from the external world actually touches the system. So if you push someone or you push a cart down the hallway, that's a contact force. You're having contact with the object or with the system. The other type of force is a field force. This is exerted without contact. So gravity is an excellent example of a field force. Air resistance could be another one. When we're talking about forces, we have the agent, which is the specific and identifiable cause of the force. So either a contact force or a field force would be considered an agent. A force can't exist without an agent and a system. So you have to have a cause of the force, and you have to have something on which the force is being applied. So to show this, we draw what are called free body diagrams. And so the first step on a free body diagram is to create a pictorial model. Usually we just represent our object where the forces are being applied to with a square. You could also circle the system, but I usually use a square to identify the system and then apply all forces to that system. And you identify every place on the system where it's touching the external world or where these forces are being applied. And you identify all of your forces, contact and field forces. So we'll draw some free body diagrams in a minute when we talk about different ways that they're being applied. The other part with free body diagrams is that you always show the forces acting away from the object. So for example, if I have an object and I'm pushing on the object, I would not show the force going towards the object like this. Because I want to show all forces acting away from the object, I would draw it this way. Okay, so that's just a little bit of a weird thing to get used to, and the reason for that is that we have all forces acting away from the object, so we're looking at everything kind of evenly. Okay, so let's talk about how force and acceleration are related. So let's say that we have a cart being pulled across a frictionless surface with a constant force. So right now we're going to ignore any sort of resistance. So if we look at a force acceleration graph, here's our force, here's our acceleration. We're pulling it across a frictionless surface, meaning nothing is acting on it the other direction. And so our acceleration is going to increase. Okay, so now let's say that we add in the concept of mass. So we're going to increase the weight of our cart. Well, think of it like if you're pushing a cart down the hallway and then someone jumps on the cart, you're going to slow down. So you would need more force to maintain the same acceleration. And so if we have just one cart, then we have a certain amount of acceleration. But now if we increase our mass, we're decreasing the acceleration. And unless we increase the force, our acceleration will keep decreasing. So if we maintain this constant force, our acceleration would decrease. So we would say that if we increase mass, we decrease acceleration, or that they're inversely related. So the slope of our force acceleration graph is going to depend on the mass of the carts. So again, here's our force and acceleration. Here was our slope dependent on one cart. Now if we double the number of carts, we're going to have that slope, and if we triple it, it becomes even less steep. And so we would say that the slope here is either 1 over m 1 over 2m, m being mass, or 1 over 3m. And so that gives us a relationship between force, acceleration, and mass. We know that slope, so let's do our 1 over m, is equal to the rise over run, which in this case is acceleration over force. And so then we can rearrange that relationship. If we wanted to solve for acceleration, then acceleration would equal force over mass. Or if we wanted to solve for force, force would equal acceleration times mass. Okay, and so this gives us that relationship between force, acceleration, and mass. Okay, so we know that force causes acceleration. And we also know that they are directly related. So if we double the force, we double the acceleration. We also know that there's this relationship with mass. And if we double the mass, we decrease the acceleration, or that they're inversely related. And so we can use that to come up with our equation that relates these three units together or these three variables together and gives us the units for force. So we already talked about how force is equal to mass times acceleration. So this is one of the three arrangements that you could use. I would put this on your note card. And so let's talk about how to find the units for force if this is our relationship. Mass in physics is usually given in kilograms. That's the standard unit of mass. And we know that acceleration is meters per second squared. So if we put those together, we have our mass, which is kilograms, and we have our acceleration, which is meters per second squared. And so we get a kilogram meter per second squared. That's a lot of units to keep writing, and so instead of writing kilogram meter per second squared all the time, we just say that that is equal to a Newton. Okay, so this brings us to Newton's second law, which is the relationship between net force, acceleration, and mass. Okay, so it says that acceleration is equal to the net force divided by mass. This is the same relationship as what we were just talking about, just rearranged differently. So we can also say that force net is mass times acceleration. So like we've talked about, this means that acceleration is directly proportional to force, meaning if you increase force, you will increase your acceleration. And that acceleration is inversely proportional to mass. So if you increase your mass, you will decrease your acceleration. So in the equation, you hopefully notice there's this net force. So far we've only been talking about one force being placed on an object, but we have these free body diagrams where we can draw more than one force acting on an object. And so the sum of all of those, or the vector sum, because they can be in different directions, so when you add up all the forces acting on an object, we call that net force. So for this chapter, we're only going to look at forces in one dimension, but next chapter we'll look at forces in the x direction and the y direction. Okay, so there's a couple different ways that we can look at net force. So let's say that we have an object, so we'll just draw a free body diagram represented by a box. And let's say that we have two people pushing on an object. So remember, we're going to draw the forces acting away from the object. And if they're pushing with the same amount, we would call this F1 and F2, then our net force would just be the forces added together because they're in the same direction. This would apply even if the forces were different amounts. So let's say that person 1 is pushing with a lot more force than person 2. Because they're still in the same direction, we would still just add them together. Okay, so now let's look at an example where there's two people pushing on an object and they're pushing towards each other or in opposite directions. So remember, we never want to draw forces acting towards the object. So if F1 is pushing on the object this direction, I would draw it here. And if F2, or person 2, is pushing with a force this direction, then I would draw them here. And so usually we designate that going to the right is our positive direction, but again, it really depends on the situation. This would be our negative direction. So our net force in this case would still be adding up all of the forces, but in this case, F1 is going to be negative. And so this would really be F2 plus a negative F1. And so our net force, depending on the amounts of each of these, would end up being smaller than each of them because we're actually subtracting. Okay, and so then the last part that we're going to talk about today is Newton's first law, which does relate to this relationship between force, acceleration, and mass, but here we're going to introduce what's called inertia. So Newton's first law says that an object that's at rest will remain at rest, and an object that is in motion will continue in motion in a straight line with constant speed, so basically as it's already going, unless an object acts on it. So these motions, either at rest or at a constant speed, will only occur if the net force is zero, meaning the object's at equilibrium. There's no forces acting on it in one way or another to change its motion. But as soon as we have a force that acts on an object, then its motion is going to change. So if no net force, we assume zero resistance, and so horizontal motion is just going to continue on forever. So if net force is zero, basically the object's going to keep doing what it's already been doing. Okay, and this is where inertia comes in. This is just another name for Newton's first law. And inertia is basically the tendency of an object to resist change. It wants to keep doing what it's already doing. So see, people's resistance to change is just natural. It's like all objects do it anyway. Okay, so if an object is at rest, it will tend to want to remain at rest. And if it's moving at a constant velocity, then it tends to continue at that velocity. Remember, the only way this could change is if we instituted a force somewhere on this object. Okay, so an object is at equilibrium if it's at rest, which would mean the velocity is zero, or it's moving at a constant speed because everything is the same. Okay, and remember we have to have a force to create acceleration. And so if there's no acceleration, then the object is moving at a constant speed. So constant speed or at rest would be equilibrium because there's no force. Net force, however, so now we're instituting a force or more than one, would change the velocity, cause acceleration, and disturb the equilibrium. So no net force, no change in speed or direction, it's at equilibrium. And we're going to ignore air resistance because that adds in another complicating factor. So we're only going to look at forces that we're applying. Okay, so here's the homework. We're going to do some examples together and discuss the notes, and then you'll have some time to work on these problems. Have a good day.